Alrighty, so we are moving on in our conversation about rocks that we started the other day by talking about rocks in the rock cycle, a few affiliated terms. Today we're talking about sort of the base or the basis of the rock cycle, igneous rocks. And this conversation goes a couple different ways. Once we talk about igneous rocks, we will move on to volcanoes, which is usually a little more enjoyable for you guys than some of this other stuff. And then there's also a video lesson that we have regarding Mount St. Helens, our most recent volcanic activity on the continent at any rate. Some of you may or may not know Hawaiian islands started erupting a couple summers ago. I mean, there's always something going on there, but it was bad. Maui got hit pretty bad. Pretty sure it was Maui. So we have a little video and activity or exercise with that. So igneous rocks in some way, shape, or form will be the topic for the next 3 or 4 lectures. I really thought I had a... Give me a second again. Really hate this bar that started showing up. That would go a long ways. Oh well. Anywho, not why I stopped. Working again? It's not working again. Okay. I updated to 17.3.1 this morning and it killed my cellular. But I seem to be getting messages via Wi-Fi at least, which is nice. God forbid nobody needs to call me. I think I have a slightly more updated PowerPoint for igneous rocks. That's why I'm doing this. Pardon me for a minute. There we go. See? The folks at home will be none the wiser. Take 2. All right, so funny, I spend so much time telling you guys that words mean something, at least they used to. And it took me way too long to make the connection between Igneous and Ignite. And I don't know, perhaps St. Ignatius as well. I don't know where the connection is there, but probably not one. Latin for fire. So, kind of cool. And I don't know about you, but when I think of igneous rocks, well, most of us probably picture a granite countertop these days. But once you remember and learn that igneous, that lava turns into igneous rock, everyone again loves volcanoes, right? So this is what we're talking about. This is what we're working with, and this is why, even though it makes me a little sad on the rock test when you tell me something like peat, which looks a lot like mulch, is an igneous rock, I do still have to chuckle a little bit because I make such a point of reminding you guys this is molten, fiery rock, and then you call a piece of mulch lava. Again, it does make me a little sad too. But think about that when you're doing the rock test, what you're calling stuff, and say, does this look like it was made by what we talked about in lecture? So really cool image of lava, and as you're going to find out really soon, when we talk about igneous rocks, we have lava and magma, right, as our two conversation pieces there. They really aren't that different other than where they're located. All right, and like I said, we'll see here in a sec. So igneous rocks are rocks made from crystals of minerals that grow in cooling magma or lava. And that can happen in one of two places. That can happen at the surface of the earth, as we just mentioned. And it could also happen inside the earth. As you can imagine, I hope, there's a big difference between something cooling off at the surface of the earth and inside the earth. The earth acts as an insulator. Okay. It takes a while for many people, me included, to realize that you could use something that we call a cooler to also be an insulator. That's why coolers are good at keeping things very cool. They're good insulators. So you can also keep things warm in a cooler as long as you don't put ice in it. But back to the point, the earth acts in much the same way. All right, it keeps that molten rock molten way longer than you would think. And as these two types of rocks are really identifiable because of their crystal size, if you think about it, a crystal is something that has to grow. It's not just a magic wand being waved and poof, it's there. Think of it like a vegetable in your garden, a head of cabbage or a carrot. The longer it has to grow to form, well, the bigger it's going to get. So we're going to see one really marked difference between rocks that form inside the earth and at the surface of the earth, and that's their crystal size. So again, magma is what we call the stuff when it's inside the earth, and lava is the same stuff outside the earth. Why do they distinguish? I don't know. I'm sure somebody thought it would be helpful, of course. Which one of those do you think we knew about first, magma or lava? Yeah, lava, right? I mean, we've been watching the earth crack open and bleed for as long as we've been here paying attention to things, and quite frequently we were scared to death of it. It's a scary looking thing, and quite often it led to villages being buried and burned and so on and so forth. So we had lava first. I have to imagine as well. I never saw article about this, but so we at some point added the word magma to help differentiate between the two. And I just want to be clear. What we're looking at here is a molten mineral mixture, okay? And yeah, I love alliteration as much as the next guy, so I could have called it a lot of different things, but molten mineral mixture. But it's not minerals yet, right? It's just elements, because what is one key aspect of the definition of a mineral that is being not taken care of here yet when we have lava or magma? What's the definition of a mineral? Naturally occurring, inorganic, crystalline. All right? So until this stuff starts to crystallize, until it starts to cool, you don't have minerals floating around there. You have ingredients. It's like calling, pointing at the a couple containers in your cupboard and calling that brownies. Any brownies yet? All right? It's cocoa powder, it's flour, it's sugar, butter, and eggs. So these are elements. This is like and the other thing I like to call it is I'll refer to it every so often as an elemental stew. All right, a lot of food analogies in there here, but it's not minerals until it crystallizes. So we got two types of igneous rocks. It'd be nice if I had a starter slide here that says intrusive and extrusive are the two types of igneous rocks, but we don't. So we have two types of igneous rocks. The first one that we're going to acknowledge is something called intrusive igneous rocks. Intrusive, inside, okay? These are the igneous rocks that form inside the earth. So they form from magma. And as we mentioned a couple minutes ago, they cool, relatively speaking, they cool slower than the stuff at the surface. And because of that, again, as we acknowledged, their crystals are going to be larger than the other igneous rocks. What we'll call in lab, and quite frequently in here, coarse grain. Coarse is in large, okay? Now, there are two other names for that same kind of rock that I don't use quite as often. And one I should use, phaneritic. All right, I should use that word. It's really the more scientifical kind of word. And then plutonic. Pluto, I'm not referring to Mickey's pal, the dog, but the god of the underworld, of course. I don't use plutonic very often. Phaneritic I should. You'll see it in your lab books. Phaneritic and aphanitic. We already know what the word A means, right? Or the prefix A, it means not. So we're looking at phanero here then. It shows up in phaneritic and aphanitic. Phanero means visible. So visible and not visible crystals, right? So large, and as you'll find out, the fine grain igneous rocks, you're really not going to see any individual crystals in them. In earth science, we're going to really just kind of graze over this stuff. In geology, of course, we go into a lot more detail of it. You guys at home in earth science will have 4 rocks. Folks on campus and the geology folks online will have 9 igneous rocks, for example. So, all right, anywho. So, crystallized inside the earth, intrusive inside, forms from magma, because magma is what we call that molten mineral mixture inside the earth. Because it's inside the earth, it cools slowly. Because it cools slowly, it grows rather large crystals. You got it? Good. And here are 3 of your favorite intrusive igneous rocks. 3 that you'll see in lab, and 3 that are just very common as well. You'll learn what those words felsic, intermediate, and mafic mean soon enough. So granite, everybody knows granite. Diorite is fairly frequently used out there. It's a building stone. A lot of curbs, actually, are made of diorite when they're just not poured cement. Gabbro, you don't see a whole lot. They don't tend to build things out of almost jet black stone. It is very pretty, though. But yeah, I'm sure many of you haven't had an opportunity to go shopping for countertops yet, but I was quite surprised and a little miffed when I went to the countertop store, and I'm wandering around. There's some really cool places. If you enjoy rocks, go to you got to go to like a distributor or something. Don't go to Home Depot or Lowe's. They just have these massive slabs, like the size of the wall in this room, of beautiful polished stone. It's unbelievable. But, geologist dork in there, and I'm like, this isn't granite. He's like, of course it is, sir. It's not composite. It's not quartzite. Those are two types of fake rock countertops. I'm like, no. I mean, that isn't granite. He's like, what do you mean? I'm like, well, where's the feldspar? It didn't have the pink. See how the granite has the pink in it there? At this point, the kid's just blinking at me. Yeah, so what they really have at the countertop store are a bunch of igneous rocks. But nobody would know what the hell an igneous rock countertop is. Everyone knows what granite countertops are. So they just kind of go with that. A lot of that stuff isn't granite at any rate. Not that you care or will care. But feel free to tell your grandmothers or mothers or whoever when they're looking at countertops. You could sound professional. It's missing the orthoclase, grandmother. Diorite Dalmatian, remember that. It'll be black and white. It doesn't have the pink. Extrusive igneous rocks. Extrude, external, extraterrestrial. That X means something. Exterior. All right? It means outside. Well, it means not from within, technically. But so these are rocks that crystallize at the surface of the Earth. As such, they form from lava, not magma. Relatively speaking, they cool way quicker than the intrusive guys. And because of that, the crystals don't have anywhere near as long to grow, so they are small, or what we call fine-grained. We have coarse-grained and fine-grained, right? Those two additional words, again, aphanitic, I am trying to use more and more. That is the proper terminology. Fine-grained is perfectly fine for you. No pun intended. For you guys, all right. And then volcanic rocks. That's just referential, kind of like the plutonic rocks. Tells you where they come from. I really don't use that, but every so often you'll see it. So aphanitic, they're not visible. When you get to seeing these in lab, you guys will definitely see the difference. It's just the rocks are going to be a solid color instead of multiple colors, and or texturally, which is actually a different conversation. But you're going to see, just not the dots are too small, the crystals are too small to see, so they blend together with your eye. So extrusive igneous rocks form at the surface of the Earth. They form from lava, which cools quickly because it's exposed to the atmosphere. Because it cools quickly, the crystals don't get an opportunity to grow very big whatsoever before they solidify, and we call those aphanitic rocks. Much less attractive, right? Rhyolite, andesite, and basalt. You're going to hear a lot about basalt. It shows up in lots of images, lots of volcano pictures. Again, extrusive igneous rocks are rocks that come out of volcanoes. So arguably we're more familiar with them, right? These are all examples of lava. Another way to think about it. If you've ever had the opportunity to go to Hawaii, one of the things they're famous for are their black sand beaches. The reason that they have black sand beaches there is because all of their rocks are black because the island itself is built out of basalt. Weathering and erosion makes sand just like it does everywhere else in the world. So you end up with blackish sand. They also have green sand, which is pretty cool. A lot of olivine comes out of igneous, these mafic igneous rocks. Yeah, very cool. I'm not belittling it in any means, but it's again one of those. Well, yeah, that's where you get sand from. So neat stuff. Neat stuff. They are old enough, of course, to have sedimentary rocks on top of them, but even those sedimentary rocks are going to be made from, you know, the base rock. So 3 examples of extrusive igneous rocks that you will see. And of course, there's always a hybrid, right? Porphyritic. Porphyritic igneous rocks have porphyrs. Does that help? Good. We'll tell you in a moment what porphyrs are. So there are some rocks that begin to cool, crystallize, as intrusive rocks. Right? They start cooling while it's magma. And then for some reason or another, that material, the Earth decides, we're going to have a volcano instead. And the rest of that material comes out at the surface, and it finishes cooling off in an extrusive manner. So what you get are some crystals that grew large, okay, and then the majority of the rock is all fine grained. All right. So those large crystals that started growing first, those are the porphyrs. All right. So that's why we call it a porphyritic igneous rock. It has porphyrs, and again, those porphyrs are large crystals. We call this in here chocolate chip cookie rock. Okay. You're going to see a nice, smooth, solid colored rock with some big crystals sort of suspended in it, for lack of a better word. Something like that. So those large black crystals are the porphyrs. Okay, so that little introduction takes care of half of the things we need to discuss for identifying igneous rocks. It's usually a nice break for you guys to switch gears into igneous rocks coming off of minerals. Minerals, you had, 4, 5, 6 sometimes properties that you were looking at. You had all this stuff to keep straight. You had multiple tables to go through. And when you're working with igneous rocks, it's a lot more like playing bingo. Okay, you look at B5. All right, well, there it is. You've got 2 things. You've got to look at the texture, which is grain size, which again we've arguably discussed. There's a few more aspects we'll add in a moment. And then mineralogical composition. Remember that felsic, intermediate, and mafic stuff you saw at the bottom of each of those slides? All right, those are your 3 columns. Igneous rock is either going to be felsic, intermediate, or mafic. Now there are a couple, again, if this were 14 weeks on igneous rocks, of course, yeah, they would take that a little further. But for a Geology 101 class, for an Intro to Earth Science class, felsic, intermediate, mafic is all we need. So I think we're going to finish up texture here real quick, and then we're going to move on to mineralogy, but I could be mistaken. We'll see here in a moment. Yeah, we're going to finish up textures. So, phaneritic and aphanitic, we already talked about those 2. Phaneritic are your coarse-grained or your intrusive igneous rocks. Aphanitic, those are your fine-grained or your extrusive igneous rocks. We talked about your porphyritic. Those were mixed grain, right? Those were your rocks that started cooling inside the earth and finished cooling outside the earth. It only works that way, by the way. You can't go the other way. So we got 2 left. We got vesicular And we've got glassy. What is my next slide? Igneous textures. Okay. That's pretty, but not hardly helpful right now. Okay, I guess I don't have slides on each of those words. So, vesicular. Vesicular igneous rocks are composed or will have plenty of vesicles. What is a vesicle? A vesicle is a pocket, all right, a pore space. Vesicular igneous rocks are full of holes. You guys know one already, I'm sure. It's called pumice. All right. And when you see pumice in lab, it is pretty unmistakable. Neat stuff. There's another type of vesicular rock that you'll see. It kind of looks like burnt pumice. Most of you aren't old enough to remember when gas grills still had rocks in them. But gas grills used to have kind of rocks in them. And it was this other type called scoria. Sometimes you'll see it in landscaping as well. It'll show up as a red, craggly looking rock. It's relatively cheap, I think. But it was used a lot. Again, a long time ago, it was used a lot when I was growing up. You still see it in some places. So there's not a whole lot of vesicular rocks out there, but they are in the right area quite common. And we'll talk about in lab how those vesicles form, why they are in the first place. And then the last texture is glassy. Glassy is, well, a glassy rock. You can do things while a rock is cooling that absolutely no crystals form whatsoever, be they small or large. And it cools so quickly. Well, the cat's out of the bag. It just cools really, really quick. That it goes to straight glass. And again, this is another one where you may not have known it was a texture, a specific thing for igneous rocks, but everyone will recognize obsidian when you see it. So, what I think I'm trying to show you here, I think the bottom left one is just, it's hard to tell that there's holes in that is the problem. So we've got coarse grained in the upper left. We've got fine grained in the middle there, the pink one. The top right is your porphyritic example. Then below that, the one on the left, it still kind of looks porphyritic. Maybe from back there, you can see that those are holes and not big dark crystals. But that's supposed to be our porphyritic. And then the last one there, bottom right, is your glassy one. Not all obsidian is jet black. There's a handful of different kinds of obsidian. We just have the black one. But there's some cool black and red striped ones. There's snowflake obsidian that has these little ash pockets in it. It's neat stuff. And again, all of these in some way, shape, or form, well, not all of these, everything but the pink one, are lavas. So, neat stuff. All right, so that was texture. Now, I don't want to say arguably more important, but certainly the more telling property is the mineralogy, okay, the chemistry. And the chemistry is important for a whole lot of reasons, not just so we're able to classify rocks, right? But they're looking at things like monitoring lava chemistries to try and predict when volcanoes are going to erupt and stuff like that, hoping that there's keys to that. We still don't entirely understand that process, okay? And certainly when things start belching and puffing out air and all that stuff, it's a fairly good indicator that something's going to happen, but it doesn't always happen. Sometimes it just does that. So they're looking into it. And same thing with earthquakes. Every so often you'll get just a little rumble. Say, oh my God, we're going to get something worse. And nothing comes of it, which is good, but scary as well. So there's a lot of these things where, as much as we know, and even they've got a chapter in your lab book, and I'll talk to you about them for an hour and a half. We're still learning about this stuff. So anyhow, we're going to acknowledge it again at this level. This is not an entire class on igneous metrology, which is igneous rocks. We've got three chemistries, or three flavors, as I call them. We've got the felsic, the mafic, and again the hybrid or the blend intermediate. All right, so you have felsic igneous rocks, you've got mafic igneous rocks, and then you have one in the middle that's a little bit of each, or transition really is even a better way to think about it. Those are your intermediates, and those are based on mineral content, which is why we took the time to learn all about minerals. You're going to see many of them again in igneous rocks when we start identifying them. This is a big, scary looking chart, I agree, which is why I really simplified the one that's in your lab manual. What we've got across the top are 7 rock names. Might recognize granite there again. All right, granite and rhyolite, diorite, andesite, gabbro, basalt up there in white. All right, and peridotite. Peridotite we won't see. It's essentially almost all olivine. In fact, I'm pretty sure that most of the olivine specimens they send us to use for mineralogy are hunks of peridotite, but whatever. So we've got your rocks up the top there. You notice off to the left, you've got that coarse-grained and fine-grained going on, your intrusive, your extrusive. So it's beneath that, then, that is the new stuff. Beneath that is the chemistries. And again, hopefully you recognize some of those terms. Biotite. We don't necessarily know what sodium-rich plagioclase is. Potassium feldspar. We've heard of feldspar, right? Quartz, we know quartz. Amphibole, pyroxene. Yeah, you actually know those minerals. For some reason, when they switch gears from the mineral chapter to the igneous rocks chapter, they start calling hornblende and augite 2 different things. And I kept those words in our lab book because I searched and searched and searched when I was writing that. And then when I did a rewrite, and then when I did another rewrite, I say, surely somebody in these intermediate or these intro level geology lab books like we have, you guys aren't meant to be majors, in geology, most of you. Surely at this level we stop confusing the students and just carry over 2 names that they know for crying out loud. But no, nobody does. Nobody does. So we get amphibole and pyroxene, and I'll have you write underneath them in parentheses the names that you knew them by. And then olivine. Okay, we know what olivine is. Good. So we have these mineralogies down here, and essentially what this table is saying, you see the vertical lines there separating granite from diorite, diorite from gabbro, so on and so forth. What we're saying is that granite or rhyolite are mixtures of biotite, sodium-rich plage, which we'll also let you know is orthoclase, speaking of using different words, potassium feldspar, which is albite, and quartz. So granite and rhyolite are nothing more than mixtures of biotite, orthoclase, albite, and quartz. 4 silicate minerals that you just learned, right? Nothing new or scary here. So you're thinking, well, wait a minute, then what's the difference between granite and rhyolite? Well, you already know that. One of them is coarse grained, one of them is fine grained. So this is why I said it's in theory a lot easier to identify igneous rocks than it was going through with those minerals. You just primarily need to look for that grouping of minerals, decide if it's coarse grained or fine grained, and boom, you've got a name for the rock. Now, of course, it's not quite that easy, but that's the theory. So anyhow, diorite and andesite then are composed of
some combination of some biotite, some hornblende, a little bit of augite perhaps, some orthoclase. I'm sorry, not orthoclase. Some albite. Potassium feldspar must be the orthoclase. I had them mixed up a second ago because it's pink. I just assumed. But we do not see any pink in diorite. Remember, I told you diorite Dalmatian. It's black and white. So, and quartz as well. Even though the quartz peters out here, you will see on many tables. That's the other thing they can't 100%. It's Mother Nature, after all. She doesn't obey our tables. We try to make tables that reflect what we see nature producing. And then the gabbro and the basalt containing, again, some a different plage now, different feldspar, this calcium-rich plagioclase. It's kind of like labradorite, but it doesn't have that cool bluish look. It's just a dark feldspar. And at this point, we don't want you to have to worry about any more mineral names. So we just call it kind of like labradorite. You all smile and nod. You're happy about that. And a little bit of olivine. Let's ignore those arrows for the moment and jump down to the very bottom. Felsic, intermediate, and mafic. All right. Again, the table that I give you is way simplified. It's got felsic, intermediate, and mafic at the top for starters, because that's sort of the point of this table. So it tells you that granite and rhyolite are felsic igneous rocks, and they're composed of biotite, albite, orthoclase, and quartz. You got it. And then diorite or intermediate. The gabbros and the basalts are the mafics. Again, we don't worry about ultramafic in here. Silicic is another word for felsic. I just don't use it because when they start conjugating silicic, they say silicious, and that sounds just a little dirty. So I say felsic at any rate. The arrows. What are the arrows for? Well, the arrows just tell us trends. All right? Trends about composition. And again, were this an entire 14 weeks on igneous rocks, we would certainly be concerned with that. Let's just start with a super easy question, okay? Olivine, quartz, biotite, orthoclase, albite, those are all what kind of minerals? Oh, and hornblende and augite. Those are all what kind of minerals? They're all silicates. These are all silica rich. All right. So this arrow here that says increasing silica content, it's just every single one of these is a silicate. And again, hopefully that makes a little bit of sense to you. We told you how many times the other day, that the majority of the ingredients are silicates. The silicate minerals are the most common minerals, so on and so forth. So it would really just go to figure. The fact that we've got potassium and sodium increasing as we go towards the felsic, and then the calcium, the iron, and the magnesium as we go towards the mafic, well, that's really probably just the primary distinctor there. Okay, what separates the felsics from the mafics. But again, not really a concern here, as these are all silicates anyhow. All right. Now we're going to get a little deep, but just for a moment, and we'll tell you exactly what we're going to hold you responsible for. It's kind of a cool concept. So, just a little review first, apparently. All right. So, lava and magma are just two terms we use for this molten mineral mixture. Reminder that until crystallization happens, we are just looking at elements, right? Also that we have three different chemistries that we acknowledge: the felsic, the mafic, and the intermediate. All right. So from there, then we've got a slightly more simplified diagram I wish I could eradicate that second column there, granodiorite and dacite. We don't really need to know about them, just like we ignored the peridotite earlier. But it is a prettier diagram, and that's one of the reasons I included it here. But again, you see the felsic, the intermediate, the mafic. We don't just draw these pretty swirls because they look pretty. What we've added in this case is that percent bar off to the left. 0, 25, 50, 7,500, see that? The idea being that the total composition of any one of these rocks could be represented by a straight line up and down through their column. Much like we have these vertical lines separating the columns, any rock that you see can be plotted, for lack of a better word, by a straight line through these ingredients. And then what that leaves you are line segments, right? If we drew a straight line, I guess actually I have drawing tools nowadays. They've disappeared now. But let's just say I drew a straight line right down through here. Okay. You would have a line segment through the white part here, the quartz. You'd have another line segment through the orthoclase. You'd have another line segment through the albite here, okay, through the biotite. Those line segments then you would measure over here. Let's say this one to this one through the orthoclase here gets you from the 0 to the 25%. It's I think, a little longer, but let's just say it's that wide. So you would say that this has a composition of 25% orthoclase. Then you would measure the line segment through the quartz, and you should get somewhere around 100%. You never end up at 100 on the nose, of course. So that's the whole point of all these swirly things, these swoopy things here, is to show you how your compositions can vary. All right. So yeah, in the end, what we're saying here is that these rock types that we're asking you to recognize are just arbitrary names that we created for these mineralogical assemblies. Okay, a rock that has this percentage of this, that, and the other mineral, we're going to call granite. Now, the reason that can work is because everyone agreed to it. All right, and they made this table and they acknowledge it across the planet. So they are arbitrary, yes, but they represent things. Every word is arbitrary, really. Chair. Why we use the word chair? I don't know. Somebody 500 years ago just made up the word chair.
It just sounded cool.
It sounded cool, exactly. Couch is another one. Horse. There you go. Well, the horse told us its name. That's just. I'm a horse. You really like the word horse? Okay.
No, I just think it's a weird word.
Horse.
Or hose.
No, you
Like
just
I think you just like words with S's in them, maybe.
Yeah, with the H and the O.
Okay. Well, sadly, there's not a whole lot more of them, are there? Hoss. Well, that's a mispronunciation of horse right there.
No, this I think there's also a slang word hoss. It's like hoss, but with the H. Or hostess.
We're learning a lot about you today.
Anything with HOS sounds weird. It's like
All right. I'll ponder that later. I will.
and just the way the horses look too, just makes it all weird.
All right, man.
Horse.
We're all going to be wandering around saying horse a little later. Yeah. All right. So, anywho, I don't even know how we got there. But, arbitrary words. So, yeah. So, I do spend a lot of time telling you guys that words mean something, but in the same sense, sometimes we did just make up, granite is granite because we decided to call it granite. That's my point. And horse is horse because, of course. Right? So, anywho. So you will, I promise you guys will have a much simpler diagram to work with, okay? But it's good to know where the simplified diagrams come from, why we simplified them in the first place. So, Excuse me. So, lava and magma are molten mineral mixtures. We've said that 6 times now. They are elements floating around in a mixture. And we're talking about them crystallizing, cooling, right? Well, there's not a whole lot of things in your everyday life that you cool and to make. Ice is pretty much the commonest exception there. We freeze water almost daily to make these wonderful ice cubes that we enjoy, right? And short of that, there's not a whole lot else we cool. So the conversation turns to melting, because we melt a whole lot of stuff. Well, at least more things than we cool. So what we're going to talk about is the fact that granite melts at 625 degrees Celsius, and basalt melts at over 1,000 degrees Celsius. Now, those aren't numbers I want you to remember. It's more so I'm showing you them for the disparity there, for the huge difference. Remember, granite was a felsic rock, and basalt was a mafic rock. So we're implying something in the chemistry there that makes one of them, for lack of a better word, more durable, okay, harder to melt. But remember, in practice here in a minute, we're actually coming down the other way. We have a molten mixture, and we want to form basalt. We want to grow the stuff to make basalt. Or we have a molten mixture, and we want to grow the stuff to make granite. So we're actually going to be coming down, but we're going to talk about it for a couple minutes from the opposite perspective. Okay? Because if you think about it, melting and freezing are two sides of the same coin. Melting and crystallizing. Water freezes at what temperature? 32 degrees. Water melts at what temperature? Good answer. Usually people will say 33, and I'm like, is it 32.1? Is it 32.000?
32.4.
Perhaps.
I think, I don't know if that's...
But my point being is that it's a knife blade, right? You're on one side, you're melting, the other side, you're crystallizing. And it's just a little change one way or the other. So we can talk about it from either direction. So, I told you we had a kind of a heavy thing to think about here, and this is Bowen's reaction series. All right? BRS for short, because Bowen's reaction series is a lot to write. Write it once and then abbreviate it, in the rest of your notes. There was a gentleman ways back, we'll just call him Mr. Bowen, who took the time to watch lava cool. Presumably over and over and over again. And hopefully different types of lavas. And what he learned from doing that was that there is a predictable sequence in which minerals will start to crystallize. First this will grow, then that will grow, then the next thing will grow, and then the absolute last thing to grow is this. And being a scientist, of course, he had a thermometer with him, super heavy duty thermometer, I'm guessing, and realized that this was related to temperature. We will crystallize this mineral until we hit this temperature, and then we're going to start to crystallize that mineral, and so on and so forth. And of course, if you have a different kind of lava, well, you might not grow that at all, but you'll grow something else for the similar amount of time. So you see what I'm saying. So not only now do we have the 3 flavors of lavas or magmas, but we're telling you that as they cool off, different things grow at different times. Now, you remember all those wonderful formulas we made you write down? Again, you didn't have to memorize them. That was good. But you do recall that they exist, right? And that, let's say, orthoclase had a completely different formula than quartz did. Or that muscovite mica was different than hornblende, and so on and so forth. Again, doesn't matter what the ingredients were at this point, but the fact that they did vary. Can we all acknowledge that? All right? Okay, good. And arguably the simplest of them all was what? What had like the leastest formula of all those silicates? Yeah, quartz. All right, quartz was silicon and oxygen. A little riffraff here and there, but for all intents and purposes, it just was silicon and oxygen. All right, cool. So this is just narrative. This is what I just said. Well, no, this is actually slightly different than what I said. So not all minerals crystallize at the same temperature. I just implied that. I said first this will grow, then that will grow, then the next thing will grow. We said that. This is new though. Minerals with higher melting points crystallize before minerals with lower melting points. So we acknowledged the idea, we introduced the idea of melting points a couple minutes ago with granite and basalt, right? One was granite was like 6 something, basalt was 1,000 something, okay? Let's say the lava itself is 5,000 degrees. I don't know how hot lava is, but let's just say it is. So it's going to cool down, and it's going to cool down, and it's going to cool down, and something is going to start to grow first. And then as it continues to cool, something's going to grow next. What this is saying is that if we were to flip it around again and try to melt this rock, well, the whole rock wouldn't melt at the same time. First, whatever the last thing to crystallize was would melt out first. Then the second to the last thing. You get it? It's the reverse. So, he's just trying to get you the idea that, again, there's not a wand being waved here and poof, you're a hunk of granite. Granite has to grow, and more so, it grows one ingredient at a time. And that's actually important. We'll show you why here in a moment, hopefully. All right, we're not going to worry about the discontinuous and the continuous branch. I'll acknowledge them in a minute. I haven't really talked to you guys about them that much in a long time, so we're just going to skip that. Okay, another scary looking table. Well, it's not so horrible. All right, so let's look at the left side where the green stuff is, first of all. And there aren't even numbers on here, so we're just going to make up some numbers. You see the temperature decreases down the left side there. So we're just going to put, again, let's say that our lava is 5,000 degrees. Okay. As we hit 4,000 degrees, the first thing that's going to start to grow is olivine. Then let's just, again, arbitrary, as we hit 3,000 degrees, it's going to stop growing olivine, it's going to start growing pyroxene. And then when we hit 2,000 degrees, it's going to stop growing pyroxene, which is augite, by the way. And we're going to start making amphibole, which was the hornblende. And then at some point, 1,000 degrees, whatever we're at, we're going to stop making hornblende, and we're going to make some biotite for a little while, and so on and so forth. But here's the catch. Here's the catch. What was in olivine? Yeah, I don't remember either, but it had ingredients, right? It had silicon and oxygen, we know that. I think it had some iron in it, and so on and so forth. So, again, you've got this molten mineral mixture, you've got this pile of goo with all kinds of ingredients in it. The entire time that is growing, it's plucking out what it needs to make olivine. It uses up those ingredients. Then once the temperature gets down low enough, it stops making olivine, starts making pyroxene. Pyroxene, I'm pretty sure, is still iron-rich, so it's still using up some iron, it's still using up that silicon and oxygen, maybe some aluminum, who knows what. At some point, you may run out of an ingredient. Let's say you run out of iron. When you get to hornblende there, if hornblende needs iron, it just doesn't do anything because it can't make hornblende without iron. It doesn't make this, hornblende light or anything like that that's just, low in iron. It doesn't make anything, so that mixture sits there until it gets to something that doesn't need iron. And let's say we can make biotite without iron. Biotite mica, remember of that. And so on and so forth. And then we get across here, it kind of skips over to the center a little bit, but look what's the absolute last thing to grow, the quartz. All right. So basically everything that's left in that pile at this point is going to pull it out and just make quartz. Same thing works if we went down the other side. This is basically the feldspar spectrum, if you would. We start making one kind of feldspar, we transition to another, we transition into another, and when we're done with all the fancy ingredients, when we run out of all the fancy ingredients, well, we just make quartz again. That's what the discontinuous and the continuous are all about, by the way. The discontinuous, you make one thing, you stop. You make another, you stop. That's the discontinuous. This one on the right, I call it a spectrum for a reason. I acknowledge that there's like a 14-week class in just igneous rocks, right? Well, you could take an entire semester class if you were enough of a masochist on feldspars, okay? You thought, what did we have, 3 or 4 feldspars? 3 of them? Okay, it was bad. There's, 30. Because of this spectrum. One just blends into another, and it's, it's a mess. It's a mess. So again, what's important here? What's important here is that these transitions are temperature based. What's important here is that as you are forming these minerals, you're using up ingredients that you have a fixed supply of. It's not like, you're getting ready for a bake sale and you run out of chocolate chips and you can run to the store and get more chocolate chips. All right? Let's just say, you're in a snowstorm and you want to make chocolate chips and you say, oh crap, we don't have any chocolate chips. Okay, I guess we're making sugar cookies. It's more like that. So once you run out of an ingredient, you're just not making anything that has that ingredient. Why don't they run out of silicon and oxygen? Again, because the dang thing is 3/4 silicon and oxygen. It's just kind of, a rigged game that way. And then the last thing I want to point out, you may have noticed that mafic intermediate and silicic there. Okay. If you flip this diagram, take that bottom right corner and kind of flip it up to the upper left corner, you have that same diagram that I've showed you 3 times now. They are connected. You have your felsic, your intermediate, your mafic going across the top, and then you'd have olivine over in the corner there where we had olivine before. Kind of neat. So there's a method to the madness, and this Mr. Bowen, Professor Bowen probably, did a lot of thinking here. And sorted this out. Of course, it wasn't just him; it was a lot of people over the years. But he gets the credit for it, first to publish, or at least first to explain it really well. So Bowen's reaction series tells us how igneous rocks are made and why we see the composition that we do. And yes, there are magmas or lavas that are mafic in composition. We said that earlier, but I just really want to come back and say that again. It's the elements that are in it that make it a mafic magma versus a felsic magma. All right? You can tell by the ingredients what kind of rocks you're going to get. So, as I mentioned, after this chapter, we go on to volcanoes. All right? So, we never really talk about the granite, the diorite, the gabbro, the rocks that form inside. So, we're going to give them 5 minutes now and sort of be done with them in short of lab. So, these are igneous rocks, the intrusive igneous rocks. And you got to wonder, well, how do you cool off if you're in a pile of magma? If you're in a big puddle of magma, how do you get that puddle of magma to cool off? Well, you can move the entire puddle All right, and by the way, they call those plutons usually. Remember we saw that word Pluto earlier. You can move this big vat of magma itself. It's kind of hard to do. More often than not, the Earth is old. She's cracked, right? More often than not, that stuff escapes through some sort of little pipeworks, if you would, through the cracks and crevices of the Earth. It's under pressure. It's down deep. It's hot. All right? It's going to squirm into whatever openings it can find. And once it does that, well, it's further away from its heat source, right? And once it's away from its heat source and arguably surrounded by cooler rock, then it itself can start to crystallize. So intrusive igneous rocks, we talk about igneous intrusions. They are intruding. And this basically just says what I just said, so we'll skip that slide. We are going to generalize, as always in this class, and we're going to talk about dikes and sills and plutons as our three kinds of igneous intrusions. Pluton we've already talked to you about a couple times. It's just that pool of magma. But dikes and sills haven't been mentioned yet. So we have two big scary words here, discordant and concordant. And if you come from a musical background, be it band or orchestra, you could even have discord in chorus, I suppose, as well. Well, actually, you get discord in chorus a lot. What is discord? No? Nobody likes music? Nobody plays music?
I don't really know what Discord is.
But you did play music?
I have a guitar.
Okay. So have you ever played with your guitar with somebody else? No. Oh, you should. It's fun. All right. Anybody? Anybody? No. All right.
Just don't like that.
Huh? Matching or not matching? It's discord. Not matching. All right, so next thing I was going to tell you is, all right, let's go back and picture 5th grade band class. Even if you weren't in 5th grade band class, I'm sure you could imagine the noise they made. All right? They honked and they squeaked and they did everything that they... Reed instruments are tough. I give them credit. Brass is hard enough, but reeds, good Lord. So yeah, that's discord, okay? You got somebody playing a little flat, you got somebody playing a little sharp, and yeah, your harmonies are not meshing. It's clashing, discordant, okay? So discordant, we're going against the bedrock. Con, for some reason, means with, okay? So concordant means you're going with the bedrock. Well, let's just take a moment, because maybe not everyone knows what bedrock is. I grew up watching the Flintstones. You guys didn't. Bedrock is that solid rock that's underneath everything, okay? You got soil out here, and yeah, you might have a rock or sticking around here or there. You're driving up north. You're going up to the Adirondacks, and you see those cliffs going up the sides, all right? That could be called your bedrock. Some people are very distinct. They say, no, we got to get rid of all that sedimentary crap. The bedrock is the igneous rocks underneath everything. That's the continental crust is the only thing that's the bedrock. We could include that solid rock that's piled up on top of it for the last couple 100 million years. Why not? All right? So the bedrock is that solid rock that's underneath all this crap that we live on. And that is usually organized, believe it or not. Again, if you've paid attention looking out the window as you're driving around the throughways and around the world here, you might have noticed that rocks tend to be layered, okay? And a lot of the rocks, especially if they're sedimentary rocks, are layered horizontally, like stacks of paper, like your book, like magazines on your table, so on and so forth. But they could be other directions as well. But they are layered. So a discordant intrusion would be a igneous intrusion that cuts through against the grain, if you allow me to borrow that word for a minute. All right? It goes against that layering. While a concordant intrusion would go along those layers. It would be like sticking a bookmark in your book. So dikes cut across the rock layers, where sills go along with it. And then a pluton, okay, again, is that feeder pool, that pool of magma deep underneath. And when we draw something stereotypical, like, for educational purposes here, it's just going to be a big round blob of something that feeds the dikes and sills. Okay? And lo and behold, you don't have to deal with one of my hand scribbles. So we got a pluton. We got that big old vat of magma at the bottom. And we've got some feeder pipes coming off of it. It's not 100% flat and level, but arguably the bedrock, the rock layers are horizontal here, right? So those vertical pipes cutting through the horizontal layers would be what? Dikes or sills? Dikes. All right? Big old intrusive dike right there. All right? And then as we go up, and yes, I know what that word means, you guys giggling in the back. And then as we go up, all right, for some reason or another, perhaps cracks in the rocks. It looks like they hit a shale layer here. Shale's nice and cracked. We hit a horizontal intrusion. All right, and those are sills. Now, sort of a nice, easy way to remember this, but again, it only works in horizontal layering, is sills. Think of a windowsill. All right, it's going to be horizontal, where a dike is going to be vertical. All right, but again, it is all relative. If these rocks were oriented in another direction, it could be completely the opposite. But for our purposes, I'm going to show you horizontally layered rocks, so that little cheat works just fine. So it leaks out into some sills, then it goes up and makes another dike again, and so on and so forth. And you can also see that this pipe work, should it make its way to the surface of the earth, it manifests as a volcano or a lava flow, whatever. Depends on the pressure behind it, how much magma is behind it. So this same pipe working system of igneous intrusions can lead its way up to a volcano. And again, over time, since it's away from that pluton now, it can begin to cool off. It can begin to crystallize and grow into rock. Laccolith, please don't worry about that. I'm just too lazy to Photoshop that word out of existence. Mainly because I couldn't get the rest of the arrow out of the way, but without a lot of work. So igneous intrusions are how intrusive igneous rocks can form. All right. Yes, they could cool in a pluton itself, but oh my gosh, all that molten stuff, it takes even way longer for that to cool off, especially if it's constantly being fed by something further down in the mantle. Usually this takes place in the crust. I didn't really mention that, but hopefully that's obvious at this point. Okay. We are up in the crust here, so this magma leaked up from the mantle in the first place. Not a whole lot to understand here. It's pretty straightforward stuff, but just make sure we're all on the same page here. Okay. Because we're going to take it one step further after I show you apparently a picture. So a lot of times these rocks are intruding into sedimentary rocks because that's primarily what we have at the surface. You may or may not know it yet, but igneous rocks are way more durable than sedimentary rocks. Okay, just the way it's like particle board versus, white pine. I think white pine's a really durable wood, isn't it? So what we end up seeing is long into the future here, when all of this limestone goes away, there's a good chance that igneous intrusion, that dike, is still going to be there. All right, we see evidence of that again as you go across the country out to where they actually have a lot of rocks at the surface. You'll see a lot more of this activity, but they're around. You drive, from here to Manhattan, you're likely to see some of this activity. So, lastly, as I said, it could come out as a volcanic event. Well, I don't have it in. Oh, that's one of the things I got rid of in this chapter. So, one thing I do want to mention. Let's go back. Oh, there's a picture of the sill. I don't know how I missed that one. So you see that dark bottom band there, dark band at the bottom. That is with the rock layering, okay? So that there is a sill. Not sure how we skipped over that. But back to this for a second. What I usually talk about next is a little bit of metamorphism. I know we have barely started rocks, and we definitely haven't talked about metamorphic rocks yet. But one of the ways to make, one of the easiest ways to make metamorphic rocks is through something we call contact metamorphism. Remember we told you that metamorphic rocks are formed from exposure to extreme heats and or pressures. Well, this isn't, believe it or not, enough to cause pressure. Even though you've got this hot magma squeezing up through cracks, arguably, pushing really hard on both sides, that's not enough. We need like continents crashing into one another to make pressure to do metamorphism. So what this is that hot. And I told you that in order to make metamorphic rocks, you need to bring the rock down into the earth where it's nice and warm, it can get exposed and stuff. Well, one other way is to bring the hot to the rock instead of bringing the rock to the hot. So what we see around these igneous intrusions are something that they call bake zones. The rock around it goes under a little bit of metamorphosis to form a new rock through, as I just said, contact metamorphosis through this bake zone here. Anyone remember what the bricks were called? What kind of rock were the bricks? Limestone. Excellent. Does anyone know what limestone turns into when you metamorphose it? It is marble. Good job. So around that intrusion, kind of like much like a bonfire, right? The closer you get to the bonfire, the warmer it is. As you back away, the less so. So all around that intrusion, you're going to get some marble forming. All right. And if again you were to see this as a road cut, like we see here, you would actually see marble on either side of that. If this indeed were limestone, it's not. But you would see marble, and then it would fade back into the limestone. The black dashity line stuff there, what's that? That is shale. We're really pressing your luck here. You're going for double jeopardy now. What does shale turn into when it gets metamorphosed? Slate. Yeah, and I heard a couple out there, so a few of you know this. All right, so again, we're going to see around those intrusions, we're going to see some slate growing, and then as you move away from it, it'll fade back into good old-fashioned shale. So that's a really easy way to get some metamorphic rocks without having to go deep, deep, deep down into the earth. All right, so anywho, this can work its way to the surface, and if there's enough magma, if there's enough pressure, and that leads us to a volcanic event and a different chapter of the book, which is where we will pick up on our next lecture.